I'm the speaker Fulin Qu, a PhD candidate from University of Sydney. My research is about the chloride binding capacity of cement, slag nanosilica mixture in seawater, sodium chloride, and magnesium chloride solutions. This is outline of my presentation. The whole presentation will divide into 5 parts. As we all know, cementitious materials, one of the most used human-made building materials, has become the preferred materials for mooring construction like the docks, sea bridge, or the wharf, and so on. However, the directly utilization of reinforced concrete has the potential risk of the reinforced corrosion induced by the high salt content in the mooring environment. There are some effective ways.
Excuse me, we cannot see your presentation. We only have the title of your presentation. If you can share your presentation, that would be great.
Okay, sorry. You can't say me. Can you say again?
Now we can. Go ahead.
Okay. There are some effective ways to decrease the potential risks of the reinforced corrosion. For example, the increasing chloride binding capacity in cementitious composites was considered to be a promised method. Therefore, in order to enhance the chloride binding capacities of cementitious composites, the slag nanosilica was adopted in this study. The deionized waters was used as a mixed water. 4 different mixed with different slag and nanosilica content were cast. In addition, the seawater obtained from Botany Bay near Sydney was also adopted to prepare the explosion solution. Except for the deionized water and the seawater as a control group, all mixture was also exposed to 9 different salt solutions with different concentration of sodium chloride, magnesium chloride, and both of them. Every group had a total 11 types of exposure conditions. Here is the flow chart for the preparing the test sample. As you can see, the mixed paste was first sealed in a 125 milliliters plastic bottle, and after 1 day, a small amount of deionized water was added. After 3 months curing, the hydration cementitious base was ground into a powder with a particle size no more than 1 millimeter. In order to obtain the well-hydration cement paste and eliminate the possible combinations, the powder was stored in a 1-liter bottle and then ended with the 13% deionized water by weight. After another 7-day storage, a 13 gram of well-hydrated powder with 15 milliliters of different solutions was whisked into a 15 milliliters plastic tube. After 6 months storage, the paste powder and the supernatant were separately and adopted for further analysis. For the chloride binding reactions calculations, the chloride concentration of seawater and the salt solution before and after seen as the exposure solutions was determined by use of altered titrators with stable nitrates and potassium ceramic solutions. The chloride binding reactions was calculated based on the original chloride concentration and the total binding chloride concentration. The result was also compared with the SRD semi-quantitative analysis and the thermodynamic modeling. The following slide will display some results about this research. Here is the pH and the chloride binding ratio result. As you can see from the left figure, compared with the deionized water, a high pH was found in seawater and the sodium chloride exposure solution, but a low pH was found in the exposure solutions with magnesium chloride. The addition of GGBFS and the nanosilica could decrease the pH of the exposure solution. This may be related to the change of the pH in the cementitious paste. Referring to the right figure, it could be found the chloride binding reactions of all mixtures in sodium chloride exposure solution was lower than than that in seawater, but the chloride binding ratios of ore mixed in the solution with magnesium chloride was higher than that in seawater. The addition of the GGBFS can improve the chloride binding ratios, while the effect of nanosilicas on the chloride binding ratios depends on the amount of dosage added. The different chloride binding ratios could be related to the different chemical binding chloride and physically binding of chloride. When it comes to the chemicals leaching behavior, the maximum element concentrations sodium, calcium, and magnesium of the supernatant for the well hydration cementitious paste after 6 months exposure are measured in this research. It could be said that the calcium leached from the well-hydrated cement paste in the sodium chloride exposure solution is significantly lower than that with the magnesium chloride. In addition, the replacement of GGBFS as nanosilicas could decrease the maximum concentrations of sodium and calcium, but increase the maximum concentration of magnesium in the same source solution. This could be indicate that the more generation of hydration gels in the mixture and in the mixture with GGBFS and nanosilicas, the less probability of calcium replaced by the magnesium. Referring to the TGA results, except for some phase change, the quantitative analysis on the contents of the CH was also conducted. After being exposed to seawater and the solution with sodium chloride, the presence of red salts could be observed. Meanwhile, after exposure to the solution with the magnesium chloride, except for the existence of red salts detected, the dehydration of bright salts and the sites could also be examined. In addition, the pozzolanic effect of GGBFS and the higher activity of nanosilica increase the consumption of the CH to form much more hydration gels. So there is a less of content of CH could be detected in the mixture with the GGBFS and the nanosilica. This is the SRD results for the different mixture to the different source solution. It could be observed the increasing concentrations of the chloride solution lead to a higher red salt content in ore mix. Especially there is higher red salt content in the mixtures exposed to the solution with magnesium chloride than those with sodium chloride. Referring to the right figure, in the same exposure source solutions, the highest red salt content was found in the PGN2 with only 13% of GGBFS, which indicates that the additions of the GGBFS play an essential role in generating much more red salt hydrate, where the addition of the nanosilica had a evidence effect on the formation of red salt. The red salt is mostly related to the chemical binding of the chloride. The physical binding of chloride is related to the structure and amount of CSH or CaSH gels. The addition of GGBFS and nanosilicas could increase the amount of the hydration gels, further increase the chloride binding capacity. For the same group, there is a lower calcium to silica ratios in the solutions with the magnesium chloride than sodium chloride. Although there is a lower calcium to silica ratios resulting in a weaker chloride binding capacities, a higher ratio of aluminum to calcium in the CaSH might increase the chloride binding capacity. A higher content of magnesium in the CSH or CaSH may also increase the physical binding of chloride. Thermal modeling by the GEMS software is also explored to predict the phase assembly for all paste exposed to the different source solution. Here is just displaying the PGN3 group exposed to different source solutions. The chloride distribution in PGN3 group is also displayed. The chloride in the bulk solutions means the further chloride ions in the exposure solutions, which was determined by the experiments. The chloride binding chemically is related to the chloride ions in flat source, and the chloride binding physically could be categorized by the two methods above. Although the PGN3 has a lower chemical binding capacity compared to the PGN2, the higher amount of CSAH and could enable the PGN3 has a higher physical chloride binding, leading to the PGN3 has the highest chloride binding capacity. There are all some results shown in this slide. In general, there are some conclusions for this investigation could be found. For the effect of the source solutions, more chloride of the ore cementation cup-dates was found to be bound when exposed to the source solution with magnesium ions. For the effect of the GGBFS, the GGBFS can improve the chloride binding capacity through the increased number of the chloroaluminates. For the effect of nanosilica, it depends on the amount of dosage of the nanosilica added. A higher nanosilica content has an evidence effect. The increased amount of CaSH or CSH and a higher aluminum to calcium ratio of CaSH in the mixtures was also supposed to promote the chloride binding capacities. Magnesium increased the amount of the chloride in the layers of CaSH or CSH, which could also be related to the pH of the exposure solution. That is all my presentation. Thank you.